Continuing to lecture on here with actually some new stuff now. So yesterday we finished lecturing on nomenclature, which again was the sort of last topic there for exam 2, which is next week. So obviously what we're talking about today will not be on the exam. So this is, I guess, exam 3 material starting here. From sort of this chapters and stuff. So we're now going to sort of switch gears. We talked about sort of bonding. We talked about nomenclature. We're now going to really talk about sort of chemical reactions and equations. So in this chapter, we're going to focus in on really chemical equations, balancing chemical equations. We will then, for the rest of the chapter, I believe, kind of focus in on different types of reactions. So we've seen some different types of reactions in some of the experiments that we did, like double displacement, single replacement type reactions. So we're going to talk about those different types of reactions, in addition to obviously balancing equations. And this is leading us into sort of the next big topic with this, which would be stoichiometry, obviously using sort of grams and moles and equations and doing stoichiometry type of problems. All right, so we will start here then and talk about, again, we're going to start here with, I think, balancing equations. So let's talk about chemical equations. Chemical equations really involve a chemical reaction taking place, and that's really a chemical change that occurs. So when we talk about really a chemical reaction, it is a chemical change, and a chemical change really means that basically what you start with changes to fundamentally something different when the reaction is sort of over. And the key there is, you can't really get back sort of what you started with by any type of physical means. So you can't like freeze it, boil it, or something like that to sort of get back your original substances. So, for example, here we have hydrogen gas and oxygen gas come together to make water. You think about just sort of regular water there, regular water, well, unlike fake water, but regular water, like, liquid water there. And you could do a lot of things to it. You can boil it, right? When you say you're cooking noodles or something like that on the stove top there. You could throw it in the freezer or make some ice cubes. But if you do all those sort of physical type changes, you will never get back the hydrogen gas or oxygen gas from which water was basically developed. But the way you can get it back is to do some type of chemical change to water and run an electrical current through it. And that again would be another type of sort of chemical reaction that would take place. So the way that we represent sort of these reactions that are taking place is through chemical equations. Chemical equations uses obviously the formulas, arrows to indicate sort of what is reacting and what is not reacting along the way here. So here we do have two hydrogen molecules reacting with one oxygen molecule to make two water molecules along the way. There's a lot of things that we do see in sort of chemical reactions, and a couple of things are important to, again, make sure we understand in terms of what is what when we look at a chemical equation. Usually on the left hand side of the arrow, those are our reactants, and that is pretty much your starting sort of material, if you will. On the right hand side of the arrow are our products, and that is basically the obviously ending sort of guys that were formed as a result of this chemical reaction. The arrow means sort of to yield or to produce. And in addition to sort of the chemical formulas that we see in equations, we also do see other type of information given to us, things like solid, liquid, gas, and aqueous, these sort of symbols next to the formulas, meaning that that's in the solid state, that's in the liquid state, obviously that's in the gas state. And aqueous we've talked a little bit about, and especially I think yesterday as well, in terms of acids. Aqueous means basically like a water environment. Now, there's usually sometimes a question about, what is sort of the difference here between sort of liquid and aqueous, right? When you look at them, they both look like they're sort of in the liquid state. And there actually is sort of a difference between liquid and aqueous. And the distinction is, if you have something that is a liquid, that pretty much means that it is kind of like a pure substance. It's by itself, nothing else is in there. So, for example, if we took just water, H2O, and that was a pure liquid, that means pretty much we have nothing else in there, just water molecules obviously present. Now, if we take water and we mix it with something like some solid sodium chloride, the solid sodium chloride will dissolve in the liquid water. And the resulting thing is you will get a solution that is a sodium chloride solution that would have the aqueous symbol. So an aqueous symbol basically means a solution, and a solution's basic definition is basically there's two parts to it. There's one part that's known as the solute, which is the smaller part. And in the case of this example here, that would be the sodium chloride. And the solvent, which is the larger part of a solution. And in this case, it would be the water. So when you see aqueous, it basically means that you took kind of two things together, mixed them, they mix well. Obviously, they are homogeneous and they make a solution. When you see something that has sort of the L designation next to it, it means it's pretty much one thing by itself. So nothing else in there, kind of like a pure substance. So that's sort of the difference between liquid and aqueous. Even though visually they sort of look the same, obviously, but there is a difference between it. Other kind of common things that you will see in chemical equations, in addition to these sort of states, are sometimes things will be written on top of the arrow here. So sometimes this arrow will have some stuff written on it. Perhaps you may see like a little delta symbol like that, or a triangle, and that usually means heat. A lot of times, this is where we find catalysts listed. A catalyst is something that will speed up a chemical reaction. A catalyst is not considered a reactant. It's not considered a product. It actually doesn't even get used up in the reaction. It's there basically to do that, to basically facilitate that reaction sort of occurring a lot faster. And a lot of times those are listed up on top. Sometimes you'll see things like, for example, metals like platinum listed up there. You might even see H plus, which means it's like an acid catalyst, or some other things sort of listed up there. In addition, we sometimes will put something up there like, for example, the reaction I was just talking about up there, or that process I was just talking about up there, which is our sort of physical change, really. Take some solid sodium chloride, and maybe sometimes people will put water up there to imply that you are dissolving the sodium chloride in water, and you end up with sodium chloride that is now aqueous on this side. So again, sometimes this process, by the way, is actually a physical process, and we can't even use, as you can see here, and it is commonly used sometimes, chemical equations to represent physical sort of processes that are occurring. Again, the process of dissolving sodium chloride in water is really not a chemical reaction. It's a physical change, because you can't evaporate off the water and get the sodium chloride back. So we most of the time use chemical equations to represent chemical changes, but they can also be used for physical sort of changes and processes as well. Any questions on any of that there? So how do we read sort of this reaction here? We could read it several different ways. We could say that there's two atoms of magnesium plus one molecule of O2 makes two formula units of magnesium oxide. Formula units, I'm not sure if we touched upon that or not, but we just kind of let you in on, I guess, what formula units mean. Formula units is typically used for a compound like this, and a compound like this is an ionic compound. So because it's ionic and it's technically not sharing electrons and stuff like that, sometimes people will not call it like a molecule or something like that. So remember, a molecule is sort of implying covalent bonding and stuff like that. So sometimes for ionic compounds, they'll use the terminology kind of formula unit to represent basically like a molecule of a covalently bonded compound. So if you see formula unit, you know, I won't say it's 100% equivalent, but it's essentially equivalent to like a molecule, basically. Also, we were talking about in the other chapter about molar mass as well. So sometimes people also, when they talk about an ionic compound, again, for the same sort of reason, it's not technically a true molecule. It's more of an ionic compound. They will also use something like formula mass instead of molar mass and stuff like that. So sometimes they'll use that sort of terminology for ionic compounds. Okay. Now, another way that we could look at a chemical reaction, our way of reading it, is the second way there, which is so it's sometimes referred to as the mole to mole relationship. And that is one that we'll see a lot definitely in this class and in chemistry, because that's really the basis of stoichiometry, which we're going to talk about in the next chapter, I think. And that is basically just using the coefficients there to tell us how many moles of each of those things we have. So we can say we have 2 moles of magnesium, 1 mole of oxygen, and 2 moles of magnesium oxide. We also can look at the total mass on each side. And again, we have that sort of conservation of mass, right? So if we add up really the molar mass of everybody on the left-hand side and add it to the molar mass of everybody on the right-hand side, we should have the same mass on each side. And that's the basis of sort of equations and chemical reactions when we talk about conservation of mass. That basically also means that essentially if we started with a couple of magnesiums on the left, we should end with a couple of magnesiums there on the right. And because magnesium is the same mass on both sides, 24 whatever it is, 31 on each side, we'll end up with the same amount of magnesium on each side in terms of the mass. So there's that conservation of elements that we see in chemical reactions. One thing that we can't do is use the coefficients as sort of a gram to gram relationship like we have there on the bottom. So we should not use that because that is not a proper relationship here. This relationship here is not correct. But if we do use coefficients, again, they do represent basically the moles. All right, so let's talk about then really balancing equations and the process to sort of go through balancing equations and, the different sort of methods that sometimes people use. For the most part, we do sort of use sort of a trial by error. So the question is, let me take a look so I can answer your question there. Let me get back there. Go. So is your question why is there no subscript over here for the oxygen? Okay, so it has to do with these are the molecular forms, right? These are basically these two elements by themselves. And remember that when these things are by themselves, as we were talking about, I think when we were talking maybe about bonding and stuff like that, and also naming, when things are by themselves, they really don't have any charge. And basically what's going to happen is this magnesium is going to, one of the magnesiums is going to really react with one of those oxygens there, right? Which has the 6 valence electrons, 2, 4, 6, we'll do it that way. And basically this guy's going to give away its electrons over to magnesium. And it's at that point that the magnesium then becomes a positive 2 charge, and the oxygen becomes a negative 2 charge, and these guys come together, and it's no longer in sort of its molecular form, its elemental form by itself, and now becomes an ion, and they will come together to make that magnesium oxide. And that's why there's 2 magnesium, because there's really 2 oxygens there. So this is happening like twice, basically. And at that point, when they come together, we're basically putting a cation and anion together, which means that is -2 and +2, which means you just need 1 of each for the proper formula for magnesium oxide. The balancing of where, we started with, say, 2 oxygens happens by putting the 2 in front. That indicates basically this happened twice, and that does give us the 2 magnesiums we started with and the 2 oxygens that we started with as well. But these kind of go from their elemental form by themselves, uncombined, to it's only really when these guys start to kind of hook up that they do gain those charges. And at that point, oxygen is no longer has the 2 necessarily on the bottom. It becomes an ion, and then we need to balance it out based on the charge. Other questions on that? Okay. All right, so then let's talk about sort of the process of balancing equations, and sort of how to go through it. So a couple important things, especially when you're balancing equations, and this may not make a ton of sense necessarily here up front what I'm going to say, but hopefully as we kind of go through some examples and you kind of do some problems and stuff on some work, it'll probably make sense to you. But the very first thing here is it's a really important thing to make sure that you do correctly. And that is, you want to make sure when you're going to balance an equation that you are starting with the correct formulas first. And what I mean by that is, if you're given something in words, for example, you want to first start out by writing all the correct formulas down, right? Regardless of trying to balance or anything like that, that really shouldn't be in your head at that point. If you have everything in words, you want to just go, okay, like you were doing sort of nomenclature, I want to make sure I put down first all of the right sort of formulas. And then you want to really get to the balancing part. And what I mean by that is sometimes people try to balance and write formulas at the same time. And what they end up doing is really screwing up, and they screw it up really badly. They end up with the wrong formulas. They end up, with numbers in the wrong spot. And they sit all day trying to balance something that will never balance because you're not really starting with the correct formulas. It's not necessarily too bad in a situation where you're given everything in words, but very often what happens though, if somebody's given and this will happen in this class, and you'll be given kind of like the reactants, and you're like, you need to predict sort of what's going to be on the product side. And, people will go, oh, there's like a 2 down here, and then they'll try to write formulas, and they'll try to write the formulas and balance at the same time. And again, they'll usually end up with sort of the incorrect formulas on the right hand side. And then they're in trouble because they'll never balance. So it's really important, even in a situation, and we will come across this here this semester, that if you're given the front part here, you just want to think about the basic sort of units that are here, forget about the balancing part, and make sure that you first are starting with, the right formulas on this side so that you then can properly balance. So that's the order at which you want to kind of do it. You want to get the right formulas and then balance. So it's really important to sort of keep that in mind. Sometimes people sort of get ahead of themselves and try to do both things at once, and it usually turns out pretty badly in terms of that. So let's take a look at one here and sort of try to figure out, what we can do in terms of balancing this equation and sort of the approach here. So let's say we had this here. We want ethane reacts with oxygen to form carbon dioxide and water. And we're going to go through this sort of process here. So again, we're given everything here in words. So we would want to make sure that we write the correct sort of formulas down first. So ethane, obviously, if you didn't know that, that would be provided for you. That's an organic guy. It looks something like this. When we see oxygen, and oxygen is sometimes worded a couple different ways. Sometimes it may be worded like this as oxygen. Sometimes it may be worded as molecular oxygen, maybe worded as oxygen gas. But basically, this is plain old run of the mill uncombined oxygen by itself. And this one, as to sort of an earlier question, this one would have the two there because oxygen uncombined by itself is diatomic. So we would have that O2 there. To form means we put an arrow. Carbon dioxide, we see the prefix there, so we know it's a type 3 as we talked about, and water here going H2O. So right now I have basically put together what is referred to sometimes as the unbalanced chemical equation. I got all of the correct formulas down. I was not concerned that, hey, there's more H's on the left there than there is on the right at this point. I just want to make sure I got everybody down correctly. And a really good way to sort of balance, or a pretty good sort of method in a sense, is to, I like to personally make like a little table and just kind of list all the elements that are present. So clearly here we have carbon, hydrogen, and oxygen, and have a side that's for the reactant side, have a side that's for the product side. And sometimes these lists, kind of can help you kind of go in the right direction or point yourself in sort of the right direction. So on the left hand side, we have 2 carbons. On the right hand side, we have 1 carbon. On the left hand side, we have 6 hydrogens. On the right hand side, we have 2 hydrogens. Left hand side, 2 oxygens. And right hand side, we actually have 2 oxygens here in the CO2. And we don't want to forget about the oxygen over there in the water. So that is 3 over there. So again, this table sort of points us to, at this point, nothing is balanced. So there's a lot of methods, but sometimes it's just easier to kind of hit the one that is sort of easiest to balance. Some people will say to start with the more complicated guys and stuff like that. But when we do balance equations, there really is 2 things that's really important first off before we get too far into this. When we are all done balancing an equation, basically 2 things need to sort of happen. And when we have sort of successfully completely balanced an equation, we should make sure that all of the coefficients are whole numbers and the simplest set of whole numbers. So you got to make sure that when you're all said and done, all the coefficients, and these are the numbers that come in front, are all whole numbers and their simplest set of whole numbers. And what I mean by that is, if you say balance this equation of like 2a plus 2b went to 2ab, although it is balanced, there's 2a's on both sides, there's 2b's on both sides, we could technically divide everything by 2 and have also a balanced equation that is this. And this guy here would be the properly balanced equation. The one above would not be really the properly balanced equation, again, because you could reduce down all of the coefficients and still get whole numbers. So that sometimes happens because sometimes people see maybe larger numbers and you will get a balance, but you can sort of reduce down those coefficients. So when you're all done balancing an equation, you got to have all whole numbers, and they need to be the simplest set of whole numbers to allow it to be balanced there. And clearly the other major thing is you need to have the same number of elements on each side. So to properly balance an equation, you got to have the same numbers of each elements on each side, and obviously all the coefficients, whole numbers, and the simplest set of whole numbers. So when we look at something like this, fairly easily, I think I could balance the carbon. And to balance the carbon, when we balance an equation, the only numbers we play with are the coefficients. So only the numbers in front. We never change any of the subscripts on the bottom. If we change the subscripts on the bottom, we are changing what it is. We never insert like anything inside a number between things. Obviously, if we change the 2 there, that would change what water is. So only the numbers on the outside. In this case, that would then give me 2 carbons. That would still give me 2 hydrogens. And now my oxygen is up to 4 in the first guy. And 1 more here for the water. That is 5 at that point. So much like what happens is a lot of times in balancing, you fix one thing and kind of screw up some other things. So then you kind of want to look and see, all right, what is maybe the best thing to balance next? And in my opinion, probably the best thing to balance next would be your hydrogen in this particular case, as because hydrogen is by itself over here, oxygen's in a couple of things over here, which means it might be a little bit harder to sort of balance. We could simply balance the hydrogen by putting a 3 in front of the water. When I do that, I still have 2 carbons. I now have 3 times 2, which is 6 hydrogens. And now in terms of oxygen, I am up to 4 in the first one with the CO2 and another 3, which would give me 7 oxygens. Any questions on that so far? At this point, I have now successfully balanced the carbon. I have now successfully balanced the hydrogen. What is left is the oxygen. Clearly, we've successfully balanced those things, and we don't want to play with anything on the right-hand side in this case, because then we're just changing numbers and going to be there all day. So we do want to look towards the oxygen on the right-hand side, and we do want to basically get it to match on the right what it is there. And on the right, we have 7, and we have 2 over here on the left-hand side. So basically what we want to do is turn this 2 into a 7. And the way that we could do that is we could actually do something like 7 over 2, like a fraction here. And if I do that, I now have 2 carbons. I have 6 hydrogens. And if you take 7 halves times 2, 2's cancel, leaves you 7 oxygens. Technically speaking, at this point, this equation is balanced. Also, technically speaking, at this point, this is incorrectly balanced because, as I mentioned up here, all the coefficients need to be whole numbers. And clearly 7 over 2 is not a whole number. So this illustrates a really good point that, sometimes along the way, when you're trying to balance an equation, you're just like, I'm not sure, you got kind of like a odd number over here and an even number over there. How do I get it to sort of balance? You can absolutely use a fraction to balance an equation. But the problem is it's not correctly balanced until you get rid of the fraction. So to get rid of a fraction, we basically got to multiply the entire equation by the denominator, what's on the bottom there. So we're going to multiply it, not just the fraction by 2, but everybody by 2. And when we do that, we end up with 2 of the C2H6 plus 7 of the O2 gives me 4 of the CO2 and 6 of the water. And if I did this correctly, we should still be balanced. And let's see if we are. So 2 times 2 is now 4 carbons on the left, 4 carbons on the right. So that's good. 2 times 6 is 12 hydrogens on the left. 6 times 2 is 12 hydrogens on the right. 7 times 2 is 14 oxygens on the left. I have 8 oxygens in the first guy here at CO2 and 6 more. That's a lot of math this early, but 8 and 6 is still 14, I hope. And we are definitely balanced. So, this is the process by which you can go through and balance an equation. Again, you saw here, I only changed the coefficients. I didn't play with anything else. and you can definitely use a fraction in certain cases. And a lot of times where you have to use a fraction, or sometimes you need to use a fraction, is in a situation like this, and not 100% of the time, but sometimes, and a lot of times where this develops is kind of like what we have here. We got like oxygen or some element and a couple of things on one side, and sort of the molecular version, kind of the uncombined version of the element that's diatomic or something like that on the other side. So that's a very common situation where you might have to use a fraction. So again, you don't always have to use a fraction, but it does happen occasionally. Um, and how do you sort of choose the fraction? Well, to choose the fraction that you need, it is pretty simple. The top number is the number you need. So if you remember in this example, the top number was I needed 7, right, to match this number. So that's why I chose 7. The bottom number matches the number of the subscript, which is this number. So these two numbers match here. So that's a very quick and easy way to figure out the fraction that you need. Number you need up on top. Bottom number should match the subscript. Probably most of the time the bottom number will be a 2. Not 100% of the time, but a lot of times it will be. Any questions on sort of the process here to balance equations? Now, again, there's many different sort of approaches or ideas as to how to sort of go through and balance the equation. And here's pretty much the step by step of what we just did. And some people, like I said, will tell you to start with the more complicated ones and stuff. I find that probably in most cases, most people do a more kind of trial and error type of thing. Add a number to the left, add a number to the right, maybe add a number to both sides at once, and kind of keep going until, if you're on the right path, at some point everything will basically come together and balance out, and everything else will sort of fall into place. Do you have to make a table when you're balancing? You don't, but it can be very helpful. You might want to, if you're not going to make a table as you're balancing, I would at least make a table or double check at the end. I can't tell you how many times I've seen people's quizzes and exams and they got numbers up there and they think it's balanced. And when you actually look at it and sort of add up left side, right side, it's really not balanced. So, just for your own safety there as you're doing the problems, you may want to take a moment at the end and just quickly just go back through and double check that everything is properly balanced. And again, you should have all whole numbers for your coefficients, and also double check that you can't go back and reduce them down to whole numbers as well, because again, that's also a very common thing that occurs. People, again, could sometimes see larger numbers and sort of balance it, and you do need to reduce it down. Any questions on that one there? All right, so let's give this one a go here. What we got up here? There we go. So take a couple minutes here and balance up this equation. Okay, so let's take a look. So again, I personally will do some tables here of what elements are present. And again, it just gives you a sort of basis to look at and see where to go, where not to go, maybe, and kind of help you go in the right direction. So on the left-hand side, we do have 1 nitrogen. Right-hand side, we have 2 nitrogens. Left-hand side, we have 1 oxygen. Right-hand side looks like we have 1 oxygen and 2 hydrogens on the left there and 2 on the right. So again, just looking at the table, clearly everything else is balanced except for nitrogen. So that is obviously a pretty good place to start. So we can simply fix the nitrogen on the left-hand side, again, by putting a coefficient, not putting any numbers on the bottom or anything like that, only coefficients here. That then gives us 2 nitrogens. It then gives us now 2 oxygens and 2 hydrogens. So again, very common. You fix one thing, kind of screw up something else along the way. But that's not a problem, because we can easily see that we can then fix the oxygen by going to the right-hand side and also putting a 2 in front of the oxygen, which is actually in front of the water in this case. In that case, it does give us 2 nitrogens. 2 times 1 for the oxygen is 2. And now for the hydrogen, 2 times 2 is 4. Lastly, we can see from our table, we then need to go back to the left-hand side here and fix up the hydrogen. And we can simply put that a 2 there as well. They won't always be 2s, but 2 seems to be a winner here in this one. We got 2, and we got 2 for the oxygen, and 2 times 2 is 4 for the hydrogen. Any questions on any of those steps there? Again, important, only coefficients. Don't change anything else. Again, don't do any weird things like I've seen in the past. People like putting numbers in between things. So only the guys in front. All right, why don't you try the next one here that you got, I think, which is this one here. All right, take a minute or two there and balance up this guy. All the same sort of approach. Looks like again here carbon, hydrogen, and oxygen. Reactant side, product side. On the reactant side on the left there, we got 3 carbons and 1 on the right, 8 hydrogens on the left, 2 on the right, 2 oxygens on the left, and we have 2 here and 1 there, so that is 3 oxygens. So at this point, again, not much balance, so very simple to fix would be carbon, kind of like what we started with on the other one. So we would put a 3 there in front. The 3 in front there does balance out the carbon to 3. Hydrogen stays at 2. And now my oxygen is 6 in the first one, plus 1 more is 7. So now we can look and see that probably the next easiest thing, again, because oxygen's in a couple of things on the right here, maybe save that there to the end. We will go with the hydrogen next, and hydrogen has 8 on the left, 2 on the right. So we can put a 4 there in front of the water. By doing that, it gives us 3 of the carbon. 4 times 2 is 8 of the hydrogen. And now in terms of the oxygen, we have 6 in the first one there and 4 in the second. That is 10, I believe. That means that we can now go to the left-hand side. And in this particular case, we got 2 on the left and 10 on the right. We actually could just use a whole number, obviously, and it would be a 5 in this case. That gives us 3 carbons, 8 hydrogens. 5 times 2 is 10 oxygen. So we are definitely balanced. Any questions on any one of those there? Okay, let's take a look at another one here. Let's see. All right, so write the balance equation for this and also obviously balance it as well. So see what you come up with. Okay, so this would be one that, everything's given in words. And again, you do want to follow what we were talking about. You want to start with the right formulas, regardless of the balancing aspect of it. So when you see diboron trioxide, that is some prefixes. That's type 3, which, as we talked about, pretty simple. Meaning di is 2, so that's a B2. Tri is 3, and that's an O3. Again, just going to lay up the formulas there. Plus water, which hopefully you know is H2O, will form boric acid, which they gave us there. So again, I just want to put in there the formulas without worrying about the balancing aspect, because now I'm going to go back and actually balance it by putting the coefficients. So again, that is the proper order. Formulas first, correct formulas regardless of balancing, then go back, fix the coefficients, and balance at that point. We can follow our same sort of method here. On the left-hand side, we got 2 borons, 1 on the right-hand side. Oxygen on the left, we actually got, looks like 4 there. 3 in the first one and 1 in the second. And oxygen's on the right. This is parentheses and a number on the outside, which means we do need to distribute that 3 to everybody that's there. So that means that we would have 3 oxygens on the right hand side, 2 hydrogens on the left. Again, distributing the 3 in would give us 3 hydrogens on the right. Not much to work with here since we only got one thing on the right hand side that has all the elements in it. So clearly that would be a good place to start. And we'll go with the boron, which means we should put a 2 there. By putting the 2 there, that does give us 2 borons. In terms of the oxygen, again, we need to distribute the 3 in. So that's 3. Then we need to also multiply it by the coefficient on the outside. So that's basically 6 in terms of the oxygen. Same thing for the hydrogen. 3 times 1 is 3, and then 3 times 2 is 6 here. Clearly, we don't want to play with anything here on the right-hand side as they're all tied together, and we're going to screw it up. So we should go back over to the left-hand side. And maybe in this case, since we do have oxygen in a couple of things, perhaps hydrogen would be the better one to kind of approach because we could easily kind of control that. And we do want to make it into a 6. So we will put a 3 in front of the water. That's going to give us 2 borons. 3 times 2 is 6 hydrogens. And in terms of oxygen, we got 3 in the first one, and 3 times 1 is 3 in the second one, gives us 6. So again, in this case, which sometimes happens a lot, by just putting the 3 to fix the hydrogen, we actually then also fix the oxygen at the same time. And this guy then would be balanced. Any questions on any of those steps there? All right, so take a few minutes here and see what you come up with on this one. Okay, let's take a look at this one. So we'll go our same approach here. Looks like we got nitrogen, hydrogen, and oxygens. Reactant and product. All right, on left-hand side there, it looks like 1 nitrogen. Right-hand side looks like 1 nitrogen. Not too bad. Left-hand side, 3 hydrogens. Right-hand side, 2 hydrogens. Left-hand side, 2 oxygens. Right-hand side, 1 oxygen, 2 oxygens. So 2 oxygens there. So doesn't look too bad. We got everybody balanced except for hydrogen. So clearly that would be a good place to start. In this particular case, we have 3 on one side and 2 on the other side. So this is not going to be a situation where you could just put maybe 1 number on one side to balance it. In this case, you would actually need to kind of put a number on each side to balance the hydrogens. In this case, you could just simply kind of multiply those 2 numbers together to figure out 6. Looks like perhaps a common number there that we could get to. So to get my hydrogen on the left-hand side to 6, I will need to put a 2 in front of there. To get my hydrogen on the right-hand side to 6, it looks like I will need to probably put a 3 there. And if I do that, we end up with 2 nitrogens. 2 times 3 is 6 hydrogens and 2 oxygens. Over here is 1 nitrogen still. And then hydrogen, 3 times 2 is 6. And oxygen now on the right-hand side, 1 in the first one and 3 in the second one. That gives me 4. So it looks so good there to begin with. I am now really screwed up a lot and fixed hydrogen, but messed up everybody else. So again, just kind of following the same sort of approach, what seems maybe the easiest to play with. At this point, probably nitrogen. Again, we got oxygen in a lot of places over here on the right-hand side. So we might as well sort of lock in the nitrogen first. So nitrogen can be easily balanced by putting a 2 there in front of the NO. When I do that, that gives me 2 nitrogens. We're still shooting 6 hydrogens, it looks like. And oxygen at this point is 2 in the first one and 3 in the second one, which is 5. At this point, I've now balanced my nitrogen. I've now balanced my hydrogen. I clearly got some numbers going on here on the right-hand side. I don't want to play with any of those. So I'm now down to oxygen. Kind of the only open spot here is with the oxygen in its elemental form. I got 2 on the left, 5 on the right. So here again, I really want to turn my 2 into a 5. So this would be another situation where perhaps a fraction would be a good choice. Again, the number on top is the number I need. So in this case, I need 5 over here. The number on the bottom should match this guy, and that should be 2. And when I do that, that gives me 2 nitrogens on the left, 6 hydrogens. Again, 5 over 2 times 2 gives me 5 oxygens. At this point, again, it is technically balanced, but it is incorrect because this number right here is not a whole number. So as we mentioned earlier, definitely can use the fraction, but not completely done with balancing this equation until you get rid of the fraction. So you definitely got to get rid of that fraction. Again, we're going to multiply everybody there by the denominator, and that would then give us 4 of the NH3 plus 5 of the O2 goes to 4 of the NO, and looks like 6 of the waters. And again, if I didn't screw anything up, we should still be balanced. So we do want to double check just to make sure. Looks like now we got 4 nitrogens on the left and 4 on the right. So that's good. We have 4 times 3, which is 12 hydrogens on the left. 6 times 2 is 12 on the right. Oxygens 5 times 2 is 10 on the left. 4 in the first one and 6 in the last one is 10. We are good in terms of balancing it. So again, we see sort of a similar situation. We got some oxygen and a couple of things on the right, some molecular oxygen on the left-hand side. Needed to use a fraction, but we didn't need to do it in the previous one, I think, or the one before that. So it's not 100% you need to use a fraction all the time. But if you find yourself sort of stuck, think about a fraction might be something that could help you. Any questions on balancing those equations there? Okay, so let's take a look at just a couple more here. Yeah. So why don't you try, let's do, write this without putting the coefficients. So let me do this. So why don't you try that one, and maybe why don't you also try this one here. Okay, we'll take a couple minutes and balance each of these and see what you come up with. Okay, so let's take a look and kind of see how you're doing. Now, in a situation like this, I personally might not go with the same sort of approach that we were doing on the previous ones. And the reason why is when I look at it, I see a lot of things that we saw yesterday. We see a lot of polyatomic ions. You know, I see like sulfate over here. I see some sulfate over here. I see some phosphate over here. I see some phosphate over here. And sometimes when you have an equation that you want to balance that contains a good number of polyatomic ions, and they are obviously look the same on each side, sometimes it's a lot easier to kind of keep those polyatomic ions together and balance them as like units rather than going, okay, sulfate there has 3 sulfurs, 12 oxygens, because there's a lot of distributing that you typically have to do when you have polyatomic ions in there. You got the parentheses around it and stuff like that. So if I sort of take that approach where I'm just going to kind of keep those polyatomic ions together, kind of balance them as units, a lot of times things will fall into place pretty quickly and you can kind of balance it relatively quickly. So what I would do is I would look at this and go, all right, well, I got one phosphate unit on the left, I got one on the right, so I don't have to worry about that too much right now. In terms of sulfate, I got 3 of them on the left, but only 1 of them on the right. And that is where I would want to start. And I could simply fix the sulfate by putting a 3 in front here. That gives me 3 sulfates, but it does also change my sodium, right? And that will tell me where to go next. My sodium now is 6, which means I should then go to the other side and fix the sodium right away. And I see my sodium is 3 here. So to get that guy to a 6, I need to put a 2 in front of the sodium. 2 times 3 is 6. Again, though, that now changes my phosphate. So now I have 2 phosphate units, which tells me where to go next. Over here to the phosphate to fix that and put a 2 in front of there. That fixes the phosphate. That gives my iron 2, which is good because I needed a 2 over here anyways. So by kind of keeping those together, you can relatively quickly balance an equation like this, especially when you have polyatomic ions involved. This is really the situation where you would do something like this and kind of just balance those guys. And what you'll see is, again, things will sort of fall into place as you kind of go from one spot to the next. Any questions on sort of that approach there? We again could take a similar approach down here. Again, we see some phosphates on both sides. We also see some hydroxide there on both sides. So we could kind of do that approach. And, you know, it's not perfect, kind of depends on what you choose. But in this case, we'll see 1 phosphate on the left, 2 on the right. So we will try to fix that by putting a 2 over here with our phosphate. 2 fixes the phosphate, now changes my copper to 6, which tells me where to go next, which would be over here to 6. 6 copper also now tells me I need 6 hydroxides. 6 hydroxides coming over here means I need to put a 3 here. Gives me 3 times 2 is 6 hydroxides and also 3 calciums, which matches over here. So, you know, it works fairly well. Clearly, in this case, if you chose to start with the hydroxide and you would have put a 2 here, you would have ran into a little bit of trouble because you would end up with 2 coppers, but 3 over here. So, you know, you could then go to the other polyatomic ion and like phosphate and you would be okay like we just did there. So again, with everything, nothing's 100% perfect, but you do still have to think about it. But it can be very quick, sort of that method. Any questions on equations, balancing equations, how to tackle equations? Again, the key things to take away is you should always, no matter usually what the situation is, if you have a chemical equation, you need to make sure it's balanced. And if you see numbers in the equation, it's probably balanced, I would say, probably in most cases. If you're given a chemical equation, you don't see any coefficients, you should probably red flag yourself there and think, I probably should make sure this thing is balanced. It may be balanced, but it may not be balanced. So you always, for most applications where we use a chemical equation, we usually need it balanced. So that's usually like the first thing you always do. And you want to make sure you're always starting with that. Any questions on any of the balancing stuff here? Okay, so we're going to now sort of transition into talking about different types of chemical reactions, some aspects of that. So the first thing we're going to kind of talk about are what are referred to as electrolytes. And there's a couple of different types of electrolytes that we're going to talk about here in the next few slides, but just sort of a preview, I guess. There are strong electrolytes, there are weak electrolytes, and obviously, as you can see there at the bottom, there are non-electrolytes. So there's basically strong, weak, and non-electrolytes. What are electrolytes? Basically, they are guys that go for a swim in water and they basically produce ions. And that's the key here. They go for a swim in water, they produce ions. Those ions, which are charge entities, positive and negatives, they help really complete sort of like the circuit, if you want to think about it that way. And it conducts electricity because of the presence of those ions that are floating around. So the presence of those kind of positive ions that are floating around, negative ions that are floating around, will help it conduct electricity really well. In some cases, maybe not so well in other cases. And that happens for a strong electrolyte and a weak electrolyte. That is what happens. There's some aspect of them when they're in solution, these guys will produce ions. A non-electrolyte, on the other hand, basically will not produce ions. So it does not produce ions. So it doesn't produce ions, and that's a key aspect as to why it does not conduct electricity. Again, in a solution of a non-electrolyte, it basically will not conduct electricity because there's no presence of ions to help kind of keep everything flowing, electrons and all that kind of stuff. Because there's no ions produced, it will not basically conduct electricity. What is the difference between these? We're going to see it on some of the other sort of slides, but just to kind of previous, since I think this slide's got some pictures that sort of relate. When we talk about a strong electrolyte, basically what that means is 100% of it breaks apart into ions. So for example, if we really have a sodium chloride solution, in solution, when you have, or you're holding basically salt water or sodium chloride, you have absolutely no sodium chloride units still together. You have 100% sodium ions that are floating around and chloride ions that are floating around. So 100% of what you have in solution are these guys. You have absolutely none of these guys still together. And because it's able to basically produce a lot of ions very quickly, when it goes for a swim, basically just hops in there, breaks apart, a bunch of ions are produced. It's able to conduct electricity very, very well. And if we kind of do a common experiment that's done sometimes is to take like a light bulb kind of hooked up with some electrodes and put it into a solution, kind of plug it in. And in a strong electrolyte, if you did that, it would be what we see here in this picture. The light bulb would go off very, very brightly because there's a lot of ions present. It's able to conduct electricity very, very well. And as you can see, very, very bright light bulb basically will go off. Now, if we had a weak electrolyte, a weak electrolyte will also break apart into ions, but it mainly stays together. So what do I mean by that? Well, if we look at something that's a weak electrolyte, like hydrofluoric acid, it will break apart into H plus and F minus in this particular case. The difference is what we have in solution is mainly this. So when you look at a solution of hydrofluoric acid, this is mainly what you have present. You mainly have the HF unit still together. But it is able to produce a little of these ions. So it's still able to basically break apart a little bit. It's able to produce some free H plus floating around and some free F minus floating around. But a vast majority of what's in that solution that's a weak electrolyte is the HF unit still together. So because it's able to produce still a little bit of those ions floating around, it's still able to conduct electricity. It's not able to conduct electricity anywhere near a strong electrolyte like we see here in the light bulb example. When it's sort of in there, this is what we see here. So this would be our light bulb in a weak electrolyte sort of situation. You can see it's still on, still got some power, still probably electrocute you, but it is definitely not as bright as what you see in a strong electrolyte. And the main difference between them is in sort of this guy over here in our sodium chloride example, we basically have, let's get something like, see, maybe that comes up. We basically have a bunch of sodium and chloride ions, pretend that's still in the water part, all floating around in there. And the difference is when we come over here to our weak electrolyte, what we mainly have in this solution is mainly HFs floating around together and a little bit of H plus and free F minus kind of floating around in the solutions. But we mainly have, again, still the whole guy still together, but the presence of the few ions that are floating around is enough to still allow it to conduct electricity and obviously still do that part of it. But again, nowhere near what we see when we kind of come over here in our strong electrolyte. Now you may be saying, well, how can you sort of tell the difference between these two? Well, one major sort of thing that will help you determine if something is sort of a weak electrolyte or strong electrolyte is actually the arrows that we see when we look at the equation. When we look at the equation that's happening there for our strong electrolyte, we see a one-way arrow. And basically what that is implying is that this reaction is going from reactants to products. Basically like a one-way street. Everybody's dumping out over on the product side. We're all going to kind of convert everybody from reactants, almost 100% all the way over there to the product side. We see a different set of arrows happening here in a weak electrolyte situation. We actually see arrows heading in both directions. And what those arrows heading in both directions imply is basically there's two directions happening. There's what is sometimes referred to as the forward direction, where reactants are going to products. And in a reaction like this, in a weak electrolyte where we have arrows heading in both directions, at some point what happens in these reactions is as you start to build up the products, so in the case of HF, as we start to build up some H plus and F minus, those guys will decide to, we're going to come back together and go back the other way. And we get some of those products now going back in the opposite direction and making more of the reactants. And that is what is sometimes referred to as the reverse direction that's happening. Basically, what will happen is at some point they will reach what is known as chemical equilibrium. And basically what that means is the rate of the forward reaction, so just as fast as it goes to the product side, will eventually equal the rate of the reverse reaction as fast as going back to the reactant side. We won't get much more into that other than that is pretty much what Chem 200B is all about, equilibrium. But for recognizing in our case weak electrolytes, basically the arrows heading in both directions is a very big indication that you're dealing with a weak electrolyte. And if you do come across something that's a weak electrolyte, you should assume that it is essentially going to pretty much stay together. And there will be a little bit of ions that are produced, but for the most part, going to stay together. Now, when we talk about a non-electrolyte, it is a substance that will dissolve. So for example, if you take something, as we will see, like actually sugar, for example. If you take sugar and solid and you put it in water, it will dissolve, right? The difference, though, is sugar is basically carbons, hydrogens, and oxygens. That is all nonmetals. That are things that are covalently bonded together. So when something like sugar goes for a swim, although it does dissolve, it doesn't break apart into like ions or anything like that. So because we're not producing any ions in that solution, what ends up happening is what we see here on our third picture. We get basically a non-electrolyte, and we are not going to conduct any electricity here because, again, there's no presence of any ions that are there. So the lack of ions here in this last one, no ions at all, means we're not conducting any electricity, and obviously perhaps will not electrocute you. Here we have a few ions in our weak electrolyte, and again we see the light bulb able to go off a little bit, and here we have a lot of ions in our strong electrolyte. Again, our light bulb goes off very, very bright. Any questions on the differences between these guys here? All right, I think that's probably a good place to lay it up here for today. So